Es ist schön, dass Sie hier in so großer Zahl erschienen sind. Ich denke, es wird sich auch lohnen. Heute werden wir den Studienarbeitsvortrag Florian Knorn, hier gerade den Beisitz noch mitgeführt hat. Das Thema der Arbeit wird uns, glaube ich, gleich selbst vorstellen, so ist es zu sagen. Er hat mir versprochen, dass es trotz der 114 Seiten eigenen Stücke
auf jeden Fall unter
Diskussion abgehen wird. Ich freue mich.
Ja, hallo und vielen Dank, dass ihr so zahlreich erschienen seid. Ich war jetzt ein halbes Jahr in Irland und werde jetzt meine Studienarbeit verteidigen, die ich dort geschrieben habe. Da ich das auf Englisch gemacht habe und auch die ganze Begrifflichkeit in meinem Kopf auf Englisch ist, werde ich das wie angekündigt in Englisch tun. Das tut mir vielleicht für die Leute, die nicht so gut Englisch verstehen oder für die ich zu gut Englisch spreche. Also, I'm going to talk about ranking and importance of complex networks, which is the title of my presentation and as well of my Studienarbeit. Special thanks to Dr. Oliver Mason on the first slide. He's the guy which I've worked most together with, and I really appreciate all he's done for me, so that's why I'm going to acknowledge his name on the first slide. Now, for the introduction, I'm going briefly to talk about graph theory. I won't go too much into details, just mention a few basic notions, move on to talk about random graphs, which are, well, random graphs, randomly generated graphs, and then finish the first section on some ranking schemes which can be used to rank nodes in a network, that is, attribute a level of importance to each node in the network. I will then, in the second section, talk about the robustness of these ranking schemes, which I then will have introduced, and robustness with respect to perturbations in the network. So you have a network, you have a ranking for that network, but then if you perturb the network that has changed a few edges, you then want to know how much will the ranking change as well. So I'll introduce a few perturbations which we can inflict onto the network, and then talk about measures of how to measure the deviation between the two rankings, and then present the results from the rather extensive simulations we have run. In the last section, I will talk about the application of until that moment, theoretical or simulated work to real data. And so I start off by introducing the data sets we will use, then mention a few words on identifying essentiality, I will talk about that later, and then present the results as well. So I will start with a few notions on graph theory. People say it started all with Euler, which tried to solve this bridge problem on his morning walks. That was in 1730, and today, big skip, it has evolved into a huge theory which has many applications, a few of which I've mentioned here. So everything that has sort of a web-like structure, you can use graphs to simulate or to model that system with. Now, what is a graph? Loosely speaking, and I say especially loosely speaking at Professor Florian, because what I'm going to say is very loose. It's a bunch of nodes, which you can see there, and these bunch of nodes are connected by a bunch of edges. Right? So some of them are interconnected. That's basically a graph. Now, you could go into more formal details, but I won't do this as it won't make any difference for the rest of the talk. It's all done in length in the first chapter of the Studienarbeit, but I'll spare you from that. Now, the way to describe a graph, you have several options. You can either use the sets, but that's not a very practical way of modeling or describing a graph, so you can use rather matrices like the JCC matrix or the Laplace, which has particular relevance. Again, not too many details on that, I won't bother you with this, but just want to mention that there are several possibilities you have. Now, what are the characteristics of the graph? This graph I've put up there is an undirected graph, meaning that the edge that connects nodes in that network is undirected, it hasn't got a sense attached to it. So there are other graphs which are directed, which have little edges in there. An example for that would be if you think of a reaction network, right? A network where the nodes are some substrates and then the edges are reactions that take place. So one node is linked to another node when this substrate gets transformed into the other substrate. And in that moment you have a sense attached to it because some reactions can only take place into one direction. You can also have double can have double edges like there, but this is all a bit more complicated than dealing with undirected graphs, and the real data we're going to look at the end is only going to be undirected graphs, so from now on I switch back to undirected graphs, please note that. Now, another issue with graphs is they can either be connected or disconnected. Connected means that every node can be reached from any other node in the network. There it's not the case because node number 7 cannot be reached from any other nodes because there's no edge attached to it. So this is a disconnected graph. A graph, if we forget about node 7, so nodes 1 to 6, that will form a connected graph. Right? Now there's another number of characteristic values associated to a graph, which either characterize the graph as a whole, also characterize particular nodes within this graph. A very easy would be the number of nodes. That's already something you can say about the graph, whether it's big or not. Then you have the number of edges, but you also have more complicated measures like node degree, or the most complicated of those, in my opinion, would be the clustering coefficient, which was quite a pain to implement, but finally we came up with a solution to implement that, because for all these measures, we also wrote MATLAB functions so you can evaluate the graphs you throw it with these functions. Now, moving on to random graphs, until now, the graphs usually have been hand-drawn in a way. And in the 1950s, very, very famous Hungarian mathematicians, Paul Erdős and Alfred Renyi, came up with the random graph model, which is basically you take a number of nodes and then you randomly connect pairs of these nodes within this network, right? Which is a very seminal model because nobody has done that before until that point. But it's a very rough model. There's no order in it. You just randomly throw in edges, so there's no order in it. And there's few practical applications, so you can't really use this network to model real networks as well. So people, for example, in conjunction with sociology, they tried to come up with another model, which would be the one by Watson-Strogatz we looked at. This is a model which has been used to model social networks, but also a few applications in biology have arisen. And the characteristics of this model is that you have a very, very high clustering, just like in social groups. I mean, we know all each other pretty much, so we form a cluster. But then you also have a few long-range connections, which could be, I know a guy from Australia, right? So he knows a few people over there, and I know, okay, I only know one person, but anyway, that's so maybe, I don't know, whatever. So you have a bunch of people that know each other, and then you have a few long-range connections. So the general characteristic of these type of graphs is, besides the high clustering, that you have very or relatively short paths. All the comparisons I'm doing is compared with the random graph by Erdős and Renyi. So you have high clustering, but a very short path length. If you want to do this with an Erdős-Renyi graph, you have to have loads and loads and loads of edges, whereas the Watson-Strogatz model is quite sparsely connected. So this is quite seminal as well, or in the late 90s. Another model people have come up with, that was Barabashi and Albert in 1996, was the scale-free model. It has a specific degree distributions for the nodes in the network. Don't want to go too much into detail, but this model allows to model, saying model very often, but anyway, this model allows you to model networks which have some sort of growth in them. Like if you look at the internet, it started out with a few computers, and then it's got more and more computers joined into and connected to the network. So this is basically also how you create Barabashi-Albert networks, that you start with a few number of nodes, and then you add in new nodes, and these attach to nodes that are already in place. Now, the thing with that is that it's also very, very short path length. In fact, it has even shorter average path length than the Watson-Strogatz model, and definitely shorter path length than the Erdős-Renyi model, still being very sparsely connected. So this is quite remarkable, and it has many, many implications because many real networks have some sort of growth in them as well. So this actually allows you to get a decent model for quite a number of applications. Now, when we have a large network, be it a real network or a simulated artificial network we've created, there's a key question you could ask, and that's who's important, who's the key player, who's the key nodes in that network, right? So one means of answering that question would be to rank. That is, you try to attribute some sort of score to each node, and then with that score you can create a ranking and say, okay, here, node G would be very important, whoever node G is. right? So, but how do you actually attribute a score in a meaningful and representative way to the nodes within the network? So there's a number of approaches. The most immediate probably would be to look at the node degrees, right? The node has a lot of edges attached to it. It's quite intuitive to say, well, this guy's got to be important because he interacts with a lot of other nodes. There are much more complicated ones like eigenvector-wise. I call them eigenvector because there's quite a large theoretical body behind it, which would be the power method. And so the hits in the PageRank algorithm, they're quite complicated, but relatively easy to calculate once you have figured out how to do it. And people, fortunately, have figured out how to do it. And today, for example, the PageRank algorithm is used in the very famous search engine Google, as you probably know. And so that's why I had the nutty professor jumping on Google over the game, right? So a number of other ranking schemes would be centrality-based. That is, node is important. It is in some sort of a center of the network. Now, how do you define a center of the network? There are different definitions for that. And with that, you can come up with different measures of centrality, and these would be eccentricity, status, and centroid value. These are quite classical measures. They've been used in resource allocation problems, and we decided to take them into our investigations as well, because centrality in a way can also be interpreted as importance. Right? Now, another thing which is quite recently being established or suggested for biological networks is damage. And I shall not describe how that works, but I have to mention that it's very, very, very costly, computationally extremely costly, which is like several orders of magnitude. For this reason, we could only investigate damage on fairly small networks, as I will tell you again later. Now, with these ranking schemes, as I mentioned in the introduction, you can come up with a ranking, but what if the graph is not the graph you think it is, right? You measure some real data, and there's always some noise attached to it, so you grab the graph, and you rank the nodes, but then it's not the real graph, because the real graph is something else you couldn't properly measure. Now you want to have your ranking scheme to still come up with the important nodes within this network. So what you want is that your network, that your ranking scheme is robust to perturbations. Now, what happens, or what would be a very, very bad thing to happen, or worst case scenario in our little ranking there would be the original network is such, and I come up with a ranking. Well, I don't know this ranking, but then I measure this original network, and I get the perturbed network, which I then rank and come up with this ranking there. But what happens if the perturbation has been such, or the ranking scheme is so sensitive that this happens, that in fact nodes are upside down. So this is like the worst case scenario, which you don't want to have. Now, this I already mentioned, I'm sorry. So the noisiness may be related to physical measurements. That can be either inaccurate measuring or also deliberate sampling. That is, you only measure up to a certain degree, because measuring beyond this degree would become more and more costly, and you don't want to get involved into this. Now, in order to actually quantify how bad the impact is, we came up with 6 different measures of deviation, I call them, which I'm going to introduce 2 later on, actually on the next slide. So basically, we went up with 3 measures of deviation which are based on the node ranks themselves, and 3 which are based just on the top percentiles of the rankings, but I shall show you that on the next slide. Now, another thing is the types of perturbations you can face. What very easy, immediate things would be like the edge remove. You just pull out edges, or you rewire edges, so that is, you just pick up one piece, one end, and rewire it to another end. Right? Another thing would be just throwing some more edges in there. That's edge addition. You can also remove nodes. This can have a larger impact than just removing a single edge, because if a node has several edges attached to it, when you remove that node, you also remove the number of edges. Now, for our simulations, what we did is, because we had to know sort of the real network, and then also the perturbed one, we couldn't take real data, because for real data we wouldn't know the real network. So this is the reason why we used simulated graphs, and we decided to take the Barabashi-Albert model, because that resembles most closely to the graphs, to the real data we're going to look at later. Now what we did is we generate and rank the Barabashi-Albert graph, so that is, you come up with rankings, say these nodes are the top 10 guys, for example. Then you perturb the graph, that is rewire edge or remove nodes, or whatever you want to do. Then you rank this perturbed network, and then apply the measures of deviation to compare the rankings. Now, those measures of deviation before presenting the results, one would be based on node ranks, as I said. So you have your original ranking over there. Those dots just present other nodes which are not of interest here. So you have those nodes being the first 5 nodes. Then you perturb the network, and what happens is that these nodes end up in different places. Now, one measure we set up is just basically look at the L1 norm of the deviation of the difference in places between. So, for example, if we look at node C, it goes from place 1 to place 9, and the absolute difference for that would be, it goes from 1. There we go, from 1 to 6, sorry. So from 1 to 6, and the difference would be 1 minus 6. You take the absolute value and you sum up, and you come up with the number there. And the bigger this number, the bigger an impact the perturbation has on the rankings. Another measure we came up with is basically look at the top rankings. Now, you have the ranking, and you consider the first 10% of the nodes in here to be important. This gives you the originally important nodes. Then you perturb the ranking, and you also look at the top 10% of the ranking, giving you a set of nodes which are the important nodes in the perturbed ranking. Now you build the intersection, you make the intersection, and then you look at the cardinalities, that is the number of nodes in these sets. So that gives you, so the bigger this set is, or the more this important perturbed nodes are actually located in this set here. So the bigger the intersection, the better the ranking scheme is, because it still identifies the right nodes. Now, that was a little bit too much detail, I think. So let's have a look at the results. This looks a bit complicated at the moment, so I shall try to tell you what we did. So again, these are representing the average values over 250 generated graphs, because we're dealing with randomness, so you want to run several experiments and average out over it. For this, we used 150 nodes and 450 edges in total. Now, these are the results with increasing perturbations. So here we remove more and more edges from the network. And up here you have the measure for the deviation. So the higher the number here, the bigger the deviation and the worse the situation is. Now, for example, damage here at the beginning seems to be a very good value because it has very little deviation compared to the other ones, but then it takes off. For example, if you look at node degree and page rank, however, they're doing quite a consistently good job, especially for increasing amounts of perturbation. Dragging a little bit behind would be hits, which is the green with the circle, and centroid value and status in here. Now, eccentricity does a little funny thing here. It seems to decrease the deviation with increasing perturbation, which is a bit counterintuitive. And this is purely related to the fact that once the graph gets disconnected, the eccentricity measure is pretty much useless. Again, more details in the Studienarbeit. But I just want to mention that this actually should continue on like that. But at some stage here, the more edges we remove, of course, at some stage the graph gets disconnected. So once it gets disconnected, eccentricity is a useless measure and does something very weird. So this is why we explain this going off here. But for the first part, it's fairly good here, because the graph's been connected up to this point. Now, this is a fairly small network, only 150 nodes. We also played around with larger networks, which would be 3,000 nodes and 9,000 edges. But again, as I said, damage is very costly to computate, so we couldn't run damage on these networks here. What you can see here, this is actually deviation measure 4, which was the second measure I described to you. You see a slightly different situation here. In fact, here the hits algorithm seems to be more robust because the deviation is smaller with increasing perturbation. And the perturbation we did here is actually add edges. Now, we don't have the problem of having graphs disconnected because by definition the Barabasi-Albert networks are connected. So if we add edges, we don't risk to disconnect the graph. So eccentricity here has sort of a sensible plot there, and we can see that it's very, very bad because it's way higher than node degree and all the other guys there. Now, try to summarize the results because we had 6 deviation measures, and we have 4 perturbations, and we run 2 different sizes of graphs, 150 and 3000. I just gave you samples. So that gives us 48 graphs, which are all in there. Some of them are in the appendix because it gets a bit boring to have too many graphs in the main part. So, but the general thing we could say about the results were that PageRank and node degrees seemed to be the most robust most of the times. However, they were challenged a couple of times by some of the other deviation measures. Eccentricity, as we've seen, is very sensitive and also quite useless once the graph gets disconnected. Damage was relatively robust, at least at early stages, but is very costly. Now, unfortunately, we couldn't give any proper recommendation, hey, always use PageRank or whatever, because there were these situations where you couldn't generalize, or where generalization would not be very meaningful. So, reasons for that we couldn't give a clear recommendation was also that it always depends on your interpretation of deviation, right? So we set up these 6 measures, but you can also come up with different interpretations of deviation. Another thing is you could use different types of perturbations, which, for example, could be combinations of these, which I've presented earlier, or you could also look at more structured perturbations. And also, another thing that will help you decide on one of the algorithms would also be the resolution of the ranking. For example, PageRank gives you a unique score to each and every node, so you can clearly say this node is better than this one. The other case would be eccentricity, which has a very, very coarse ranking, very clustered ranking, and it just gives you basically 3 groups of nodes saying, so these are top important, these guys are well average important, and these guys are not important. So this is a very poor resolution, and sometimes if you need high resolution, eccentricity wouldn't be your choice. Another thing, of course, is the interpretation of importance, right? Until now, I've only said you have those ranking schemes, and they decide on which nodes are important. But has this importance, does it mean anything in real life? So in order to judge on that, you have to look at an application. This application we did, of course, with real data. That's what the name suggests. And the key question we wanted to ask, now the nodes that are ranked importance, does it also correlate with real importance in some application? So it always depends on the application, as I said. The application we were looking at then was protein-protein interaction networks. These are all undirected graphs, so you have proteins, they interact with each other, they form the nodes, and they are connected if they interact in some sort of another. What we also needed to do is isolate the largest connected component. I want to leave it at that. The data sets themselves were large disconnected graphs, so what we did is we took the largest connected cluster out of the graph because we needed connectedness for measures like eccentricity, and ignored all the nodes that were not attached to this big main body of the data set. And we then try to answer the question if top-ranked nodes, they are essential. Essential here means that they are essential for the survival of the organism. So if you take out one protein or target one protein, if it was actually yeast, if it would die or not, that would mean this protein is essential or not. So we tried to see how does top ranking correlate with essentiality. To answer that question, again, we set up 2 sets. One would be the vertices which are essential, which are known to be essential. These the biologists have given us together with the data set. And then we also look at the set of nodes which are judged important by the ranking schemes. And again, we look at the intersection and hope that the intersection with both sets is as big as possible. But there's one important benchmark, which is of course the fraction of essential nodes within the entire network. So if you have, say, 1,000 nodes network, and there's 100 nodes known to be essential, so that would mean about 10% of the nodes are essential. If a ranking scheme actually only gives you 5% of essential nodes, you'd be better off just randomly picking nodes instead of actually applying the ranking scheme. Right? So the absolute benchmark is the total fraction of essential nodes within the network. Now, as I said, that would be yeast. This is the technical Latin term for it, I guess, which I shouldn't try to pronounce. On the right side, you see a representation, a graphical representation of the UTS data set, which appeared in a Nature article, or together with the Nature article in February 2000. It has 500 nodes, and the essentiality, well, the fraction of essential nodes is 22% of that. Another data set which is bigger, way bigger, is the data set by Ito et al. And the third data set, which is gigantic for our standards, was on about 4,500 nodes and has been established by Yu et al. In an article for genetics. Now, what we did, I told you we take the top fraction of the nodes from the ranking. Now you have to decide what top fraction is considered important, and we decided to say 5% of the top ranking is important. Of course, that's an arbitrary figure, and it really depends on the application. But as we're not biologists, we said, okay, we're happy with 5% of nodes. Now, what we could see is that PageRank and node degrees are most adept. We could judge all that through these type of tables. There's also a number of these in the Studienarbeit, and they actually show you the fraction of essential nodes among the top ranked nodes given by the ranking scheme, right? So here, the roughly 50% means that if you take the top ranked 5% of nodes from the PageRank ranking, from these nodes, about half of them are known to be essential. So the success rate for the PageRank algorithm in that setup would be about 1 in 2 nodes. So, as I said, node degree and PageRank are mostly adept. I marked in bold the figures which are best figures for each data set. And we can see, for example, again, damage when we lacked the nodes because they were too good, they were too large, the networks. But looking here at centroid value and status, for instance, they were only a fifth of the nodes, of the top ranked nodes, were in fact essential. And this is actually a very, very bad figure because it's below this essentiality threshold, meaning you'd be better off just randomly pick 5% of the nodes, and you'd have more chance to actually picking essential ones than actually going through the trouble of applying the ranking scheme. So status and centroid value gave us mixed results. By mixed, I mean, if you look over here, it's actually a very good figure, very close to the winner, which would be PageRank there. Now, further investigations are needed for damage. I mentioned that earlier, it's very costly and we couldn't run it on these networks. Another thing we looked at was the robustness of this identification process, again with respect to perturbation in the networks. So, again, as I said, data is usually inaccurate to some extent, and we wanted to study the effect of edge perturbations. Again, we could see that PageRank and node degrees gave us still the best results, but hits was the most robust. Now let me explain that. Here we get again the figures, the fraction of essential nodes among the top ranked nodes by the different ranking schemes for the different data sets. You could see again PageRank gave us the best results. Here's again the essentiality threshold, but none of the nodes fell below it, which is a good thing. Okay, this one there did. What I mean by most robust is that hits always identified the same nodes. It didn't identify a hell of a lot of them, but it always identified the same nodes, which is a good thing, right? So you perturb and it still comes up with the same guys in a way. So this was a very interesting result. But as I said, PageRank and node degrees gave us the best results in there. Now, I shall come to the conclusion of my little talk and the Studienarbeit. So what we did in the first 3 chapters is developed a whole number of different functions, MATLAB functions that you could apply to graphs and giving you those characteristic values or drawing you the node degrees, or also calculate the ranking schemes, calculate the rankings actually for the different schemes. What we could then see is when we evaluated the robustness of the ranking schemes is that PageRank and node degree usually were most robust, usually because it has been challenged a number of times, and that eccentricity was rather not very suitable. Another thing is when we then applied it to real data, we could see again PageRank and node degrees usually did a good job. Hits, however, was the most robust. Now, a thing is which personally surprised me most during the work is that the node degrees did a very, very good job, right? The node degrees, you get them right away. You just look at the adjacency matrix, you sum up the elements, and then you know what degree node is, or you can just look at the graph and see, okay, there's 5 edges attached to a particular node, so it's got node degree 5. There's no algorithm you have to run, there's no iterative process or anything. You just get the result right away. And with this totally uncostly ranking scheme, you get very good results, same as PageRank, which is much more costly. So that was a bit surprising. Now, a number of things which I personally and humbly would recommend for further investigations, if somebody would be interested in it, is to, of course, evaluate other ranking schemes and also do a little bit more investigations for damage. That should be done, in my opinion, through a proper implementation in C, which is a lot faster than doing it in MATLAB. Another thing people should try to look at is different deviation measures. I came up with 6 of them, which is okay, but once I've done all that, a lot of different approaches also popped into my head, but at that stage it was too late. But I might do it later, maybe. Another thing which I would recommend is have a look at more structured perturbations. That is, not just randomly remove edges, but say, okay, I want to pick out the most highly connected nodes. Now, this is not a very real-life type of situation, because in real life, if you target nodes, you usually don't know which are the most connected nodes. At least the bacteria wouldn't know which is the most highly connected nodes among itself. But this is another thing one could look at, especially in the background of, for example, the internet, when people, when hackers try to attack highly connected computers, which would be important computers on the internet. Then one should see what effect that has. And of course, other data sets should be focused on, and also directed graphs, which we haven't done. Final slide is, I would like to say a few thanks again to Ollie and Bob, and also to all the Hamiltonians, which are my fellow workmates at the Hamilton Institute. Kai, one of them. And I also would like to thank Jörg and Janine, which is outside, hopefully preparing the coffee. I'm very grateful for that. And I would also like to thank the Studienstiftung and the Science Foundation of Ireland with this cryptic grant number. It's important to mention that because they funded my stay there. As you all probably know, Ireland is a very costly place to live. I also would like to thank my family and close friends. My dad's over there. Thanks a lot for your help. And of course, to you, you're such a nice audience.